We have some legitimate assignments of probabilities to a die, to the faces of a die. So these would be probability distributions that you could use for dice or a single die that are considered legitimate and haven't broken any rules. So here's the first one. The first one is the typical one we use. This says we have equally likely outcomes. So all of them are the same number, and the sum here, 1, 6, 1, 6, they add up to be 1, like they're supposed to. So it's good. They're all probabilities, they add to be 1. This second one here has the same values as a regular die, except it looks like 1 never happens. 4 happens half the time, and the other values are equally weighted. 2, 3, 5, and 6 happen each 1/8 of the time. The sum is 1. You're allowed to have 0 or 1 is one of the probabilities. And so that's considered legitimate. And the extreme case of legitimate is this one here, which really isn't random. Because 1 happens all the time, and these other ones never happen. So you could have that happen if you happen to be holding a die that has 1s on all the sides. You just didn't know it. You start rolling it. You just get 1, you get 1, you get 1. And then you go, hey, wait a second. What's going on here? But it's legitimate. It's not considered random probably, but it doesn't break any of the rules. So you wouldn't use probability to analyze the situation, but it is a distribution that could be called a probability distribution. Technically it's not random, but it is a probability distribution. Here are two that have made some errors and broken the rules in terms of what you're allowed to do in assigning probabilities to outcomes. Same 6 values. Here it looks like they're equally likely, but they sum to be less than 1. That's no good. So if it sums to be less than 1 or greater than 1, it's not considered a probability distribution. So we have one on our sheet that has 1/7 for all of these. 1/7? This is greater than 1, is that right? This sums to be 6/5. It's greater than 1. There's one on the sheet that's 1/7 for all of them. It sums to 6/7. It's less than 1. The sum has to be 1. So bad. The sum P of X equals 1 fails. Downstairs here's another one. Now these numbers sum to be 1, fine, because 1, 0, minus 1/2, 1/2, 0, minus 1/2, third, a third, a third. The sum is 1. But the probabilities aren't really probabilities. So this one here, being negative, isn't a probability, so that's not a legitimate probability distribution. Over on our next slide, we wanted to draw some pictures. We said you can, if you have a discrete random variable, you can analyze its probability distribution by making a table of values, but you can also have graphs. And you can also have formulas. So here's two types of graphs people use for discrete random variables. One is a line graph. You have a number line here. You identify your values on the number line, and you make little lines up like this, whose lengths match the probability. So this should say probability here. So they're skinny little lines because, well, maybe the thinking is, you can only get the value 1, right? You can't get something over here, so there should be nothing over there, just be over 0, 1, and 2, and 3. That makes sense. On the other hand, sometimes something's discrete because of rounding, in which case the 0 could represent numbers near 0, and the 1s could represent numbers near 1. So we're allowed to make histograms like this, where the bars extend past the actual observed values, if we're thinking maybe there's rounding, or maybe we just don't like the look of this. This is prettier. In this particular case, the sum of the areas comes out to be 1. That's convenient because these bars are width 1. The heights are the probabilities. And so we'll be seeing graphs like that when we talk about other kinds of experiments where there's integer values that are the random variable takes on integer values. And then if we make graphs over those integers where the bars of width 1, then the areas of the bars sum to be 1, which is something we're going to want to look at graphs where the areas sum to be 1. We've seen that we use area to represent things in the past. Here we could use areas to represent probability. And there's a lot of stuff happening on this slide. Here we go. We're going to find a formula for the mean of a discrete random variable. Mean of a discrete random variable, like that. The formula is here. You compute the mean by summing values times probabilities, and we'll do some of these in a second. The name for this mu is also sometimes called the expected value. It's called the expected value because this matches what we would expect if x bar was computed from a huge number of observations, say n observations, a big number. And then we imagine what would happen if we computed the mean. We'd say, well, each value would appear about n times its probability number of times. So if, say, x had probability 1/3, you did a million observations of the experiment, about 1,000,000 times 1/3 times you should see that particular value. And if you summed up the x's, each value would appear this many times in the sum. And so if we sum those values times number of times, we sum those up totally, then we ought to get an answer for the sum of the x's. It should be about this. And then if you divide by capital N, these n's cancel, and you get our formula, sum of x times p of x. So we'll investigate that on future slides, but right now I've run out of space, and we're going to move on to the next slide. Here we go.